All right, so we're ready to talk about the fundamental theorem of calculus. We're going to see that there are two parts. Which one we refer to part one as part two is not terribly important, and I hope that after you see both parts, you'll really see these as kind of unified as just the fundamental theorem of calculus. But since we're covering this one first, I'll call it part one. In some text, it's referred to as the evaluation theorem. And what I'd like to do in this video is not only state the theorem, but really see why it holds true. In order to do that, let's first review a theorem called the mean value theorem, which I'll abbreviate MVT here. So I have the statement written here that by that theorem, we say that if f of x is differentiable on the interval, the closed interval, from a to b, then there must exist a point c within that open interval such that f prime of c is equal to f of b minus f of a over b minus c. So, I should b minus a, what is c? Okay, so let's think about this first of all, just to get an idea of, again, maybe visualize what this is saying. So if I have a function f of x, importantly, a differentiable function, then we can think about placing some of these things on there. Let's assume that my a is here and my b is here. This is f of x. And let's think about how we can illustrate on my graph these different things on the left here. And let me maybe do a better job of calling that a. Okay. So when we're looking at this, let's think about, first of all, the thing on the right. So this I will make blue. So that is exactly going to be the slope of the line that connects these 2 points on the graph, the one at A and the one at B. And we call that the secant. So that's the slope of the secant line. And again, I can think about drawing that line. So we have a visualization of what the slope means there. So what this is saying is that between A and B, I should be able to pinpoint a number C, or a point C, at which the line tangent to the function is parallel to the secant line here. So this is the slope of the line tangent to f at C. So imagine that you can run your pen or your pencil along this line here, and you want to find the point at which you see that your writing instrument is parallel to the blue line. So if I were to do that, it looks like that, I guess I drew something relatively symmetric. It kind of seems about halfway, that I would be able to sketch the tangent here, and in this case, I would have identified a C value. And so that's what we're getting with the mean value theorem. Now, importantly, notice that it says that there exists a point. There could exist many, many points, infinitely many points, where that's true, and that's okay too. So just thinking about here that I've drawn a picture where there's just one point where that seems to hold true, and this is just eliminating the possibility of no points. The other thing that's really important that I want to focus on throughout this course is when we have these kind of conditions in a theorem, to really see why that's important. A nice example to consider of a function that's not differentiable, where you can see that this property does not likewise hold, is the absolute value of x. Right, so if you were to look at the absolute value of x, we know that that's not differentiable at 0. And consider the a value to be -1 and the b value to be +1. If we were to think about the secant slope that connects these 2 points, well, the secant slope would be 0. But there's no point between -1 and 1 at which the line tangent to the curve has slope of 0, right? We might be tempted to say that that happens at the origin, but it doesn't, it's not differentiable there. So this example is just to showcase kind of why differentiable matters in order for this condition to be true. Okay, so the reason I brought that up is we're going to actually see how the mean value theorem can be used to prove the first part of the fundamental theorem of calculus. So I've written here the statement of the theorem. If f of x is continuous on the closed interval from a to b, and capital F of x is any antiderivative of little f of x, then we can say that the definite integral of little f from a to b is equal to big F of b minus big F of a. So there's a lot of information to unpack there. This, first of all, when we start to refer to this antiderivative, capital F, I've put in parentheses that just means that if you take the derivative of big F, you end up with little f. And when we say any antiderivative, that's reflective of the fact that if I have the antiderivative of x, well, we typically say x squared over 2, but you could have any additive constant on there and it would still be an antiderivative. So regardless, this theorem is going to hold. For any of those antiderivatives, your difference that you get on the right would still be the same. Additive constants would cancel. And what I want to do here is see why this is true. And in order to do that, not only we're going to use the mean value theorem, but also we have to rely on our knowledge of the definition of the definite integral. So coming back to that idea, let's start now and think about how we're going to be able to do this. So let's let delta x represent what we've continued to do here, b minus a, the length of the interval divided by n, and xk to be a plus k delta x. Then in order to show that this equation holds true, we need to show that if I take the limit as n approaches infinity of the sum from k equals 1 to n of little f of x k star delta x, which remember, this is how we defined the integral from a to b of f of x, we need to show that that limit is capital F of b minus capital F of a. So that's just another way of reframing the desired end result here. So what I want to do is break this down into steps where I can get from the left edge to the right edge in some sense. So one thing to consider is the connection. So you can see that on the left-hand side, we're involving little f, and on the right-hand side, capital F. So we need to bridge that in some way. And we remember that big F is the derivative of little f. And we can connect these by the mean value theorem. So by the mean value theorem, first of all, when we're looking at the function big F, first of all, we know that big F is differentiable simply by the very notion that we've defined it as an antiderivative. So the mean value theorem is applicable to big F because it is differentiable. So by the mean value theorem, there exists some point xk star. Let's see if I can write that a little bit. In the interval from xk minus 1 to xk, such that if I take, let's see, let me write it the same way we've written it before. So let's pause first of all a moment. I want to emphasize here that this is playing the role of C. The reason I'm not simply calling it C is notice that we're going to iterate this n different times over my subintervals. I have n subintervals here. So in each subinterval, I want to find an appropriate value of C. In order to differentiate those from one another, I'm going to call it x sub k star so that the k is specifying which subinterval we're in. So think of that as C. And if we go back up to my mean value theorem, we have this statement here that we're going to say that at that C value, the derivative of the function, so the derivative of big F, so instead of C, I'm writing sk star, that should be equal to the slope of the line, the secant line, through xk minus 1 and xk. Okay, that is directly stating the mean value theorem, and I'll point out the other connection here is my interval from A to B is being replaced by my interval from xk minus 1 to xk. Okay, so that's directly stating that. Let's use this to rewrite this a little bit. First of all, capital F prime is defined to be little f. The derivative of big F is little f. That's in the IE statement up here. So I can replace the left-hand side with that. And the other thing we can take advantage of is the denominator here on the right-hand side is xk minus 1. Well, that's exactly how we define delta x. So thinking about that, that's that common jump that we take to get from one x value to the next. And so then I can rewrite this to say that little f of xk star times delta x, so multiplying both sides of my expression by delta x, is equal to capital F of xk minus capital F of xk minus 1. So that's what we get from the mean value theorem. Okay, so let's go back to the desired goal. So remember, we need to show that the limit of this sum is equal to big F of B minus big F of A. Well, at this stage, I've just seen a way that we can rewrite this part from the mean value theorem. So that is now equivalent to this from the mean value theorem. So let's think about that for a moment. The sum from 1 to n of little f of xk star delta x is equivalent to the sum from k equals 1 to n of big F of xk minus big F of xk minus 1. That's what we get from the mean value theorem. So let me just kind of chunk this part. Call that from the NPT. Let's think about this new sum here. If you were to write out the terms of this, starting with the first term, well, you would get f of x1 minus f of x0. And then the next term would be f of x2 minus f of x1. And the next one would be f of x3 minus f of x2 dot dot dot. And if you think about the last several terms, you would get an f of x n minus 1 minus f of x n minus 2 plus f of x n minus f of x n minus 1. So all I've done here is just kind of written out, to some extent, the terms of this sum with the ellipsis notation to say there are kind of things in between. But let's think about what happens here. I have a positive f of x1 and a negative f of x1. I have a positive f of x2 and a negative f of x2. Yes, I have a positive f of x3, but I also, hidden in the ellipsis notation, there would be a minus f of x3. It would be in the next term. Likewise, you can see that the f of xn minus 1s cancel, and this f of xn minus 2 would cancel with something in the ellipsis notation. But we're left with two things that don't cancel. And that's what I really want to highlight here. There's no cancellation of the kind of extreme values. We call this a telescoping sum, and we're going to see more of this later. But what this actually simplifies to is f of xn, which is the positive term, and there's a minus f of x0. But that's the same thing as just f of b minus f of a. If you think back to how we define xk, when we talked about Riemann sums, the x sub 0 term was always the leftmost point of the interval a, and xn was always the rightmost point of the interval b. So at this point, we've now shown that this is equivalent to this. If you look back at what we wanted to show, we wanted to make a statement about the limit. So at that point, if I have an equation, we could take the limit of both sides and say that the limit of my Riemann sum must equal the limit of the right-hand side, but this is a constant. Capital F of B minus capital F of A is constant. If you take the limit of a constant, the result is that very same constant. So sure enough, we get that that limit of Riemann sums is equal to big F of B minus big F of A. So making the connection back to how we defined the definite integral, that suffices to say that the definite integral from a to b of little f of x is equal to big F of b minus big F of a. And again, just to emphasize once more, big F is just representative of any antiderivative you can find for little f of x.